Hello! So I wasn't really feeling like doing hexadecimal type videos, so I decided that that'll be in a later video, or even in a different series. I don't even know if it's right for this series, but the good news, apart from hexadecimal, is that we'll be starting logic gates today, which is one of my favourite topics for the basic ideas behind computing. So let's start off with some nice and simple explanations. The idea of a logic gate is to put two inputs in and you'll get an output that you can predict based on whatever logic gate you're using. Actually, the definition of a logic gate is very similar. It's an elementary device used to predict a predictable. I'm sorry, I completely messed up. Let's start again. An elementary device used to produce a predictable output based on the input combination. That is, two inputs produce one output, and based on what logic gate you're using, you can predict it. After Gottfried Wilhelm Leibniz, that's a very weird name, refined the binary number system in 1705, Charles Sanders Peirce described how logic can be carried out by tiny switching circuits in a letter in 1886. Many attempts were tried after this point to create these theoretical circuits, although it wasn't until Walter Bode, I think that's how you say his name, came up with the first electronic version of the AND gate in 1924. That explanation might not have been too much help, but essentially what I told you there was that if you put two inputs into a logic gate, you get an output, and there were a bunch of people who decided, hey, we can do this with circuits. So a better explanation might be that either the inputs can be a 1 or a 0, like in binary where we said you can have a 1, an on or an off. So that means the output can also be 1 or 0. So this whole thing kind of works in base 2. There are many logic gates, both regular and irregular ones. The regular logic gates include things like the NOT gate, the OR gate, and the NAND gates. The irregular logic gates, on the other hand, include weird things like truth gates or false gates. They're mainly theoretical. A few of them exist. They're just not particularly useful, and you usually create them by accident in real life. You wouldn't use them too often. Alright then, so we've explained the ideas behind logic gates, a combination of inputs to get an output. We've explained how the inputs go in and how the output comes out with a 1 or a 0. It works in base 2 in binary. But I haven't really explained each individual logic gate. For example, what is a NAND gate? That doesn't mean anything to you. What's the combination of inputs? What's the combination of outputs? Or what's the output based on the combination of inputs? What is the NOT gate? What is the XOR gate? What is the NAND gate? You don't know any of these yet. So I'm going to hop into Minecraft because it's a lot easier to explain logic gates with a simulation. I certainly can't explain logic gates just by you guys staring at a PowerPoint and me telling you what's on the PowerPoint. So I'm going to go into Minecraft and hopefully you get a better understanding about what each individual gate does. Okay then. So I'm inside Minecraft 1.9 right now. Oh, there seems to be a problem to record. Let's stop this recording for 1 second and see if we can fix that. Okay, so I am having to do this like this. I'm going to explain logic gates right now. So this is the NOT gate. It's the most simple logic gate that you can make in Minecraft. Basically, it gives the inverse of whatever you put in. So if you put in a 1, you get out a 0. If you put in a 0, you get out a 1. They're complete opposites. There you go, I'm demonstrating this now. As you switch the input will always give the opposite of whatever you put in. This is the AND gate. You need both of these levers to be on in order to get the output. If you put one on, it won't come on. If you put the other one, it still won't come on. You need both inputs and then you get an output. That's the idea behind the AND gate. So that's the combination, both or nothing. So here's the OR gate. You can have one or the other, or both. It doesn't really matter. Any combination will give an output except 0, 0. Here's the XOR. The XOR, slightly weird. This is it. So there, you have to have one or the other. However, if you have both, it will turn off again. So basically the idea behind it is that both inputs have to be different. If they're the same, it will be off. Now let's talk about how you invert the AND gate to make an NAND gate. So here you go, we're putting a NOT on the NAND gate to invert it. So now we need both to turn it off. We don't need both to turn it on, we need both to turn it off, which it is the inverse, it works. There you go, there's a NAND gate, and an AND gate is just the inverse of a NAND gate. So there we are, guys. It's the end of the whole unit. We've covered the whole of the whole logic unit. So in this unit we covered number systems like base 2 and base 10. We also covered logic gates. As an addition to the logic unit, I plan on explaining how the hexadecimal is used in computers. Like I said, it might be for another series. Also I'll probably use Minecraft for that because it is very easy. However, I don't think that I'll go over the irregular logic gates that I use because, as I said, they're not very much use to us. They're very confusing as well. So I've now explained logic gates in this specific episode. I've explained every single logic gate, the combination of inputs you need to get the output to be 1. And next time I'm going to talk about not hexadecimal. I'm not going to talk about hexadecimal, but I'm going to start with a little bit of history about the arithmetic logic unit and the CPU. So I hope you've enjoyed, but more importantly, I've hoped you learned.